Good morning, everybody. Thanks for joining us. My name is Kevin Renaud with Peerless. We are having a bunch of people still coming in. Typically, we just wait another minute or so. There's a lot of material to cover here today, so we won't keep you waiting too long. All right, we're going to go ahead and get started. Again, my name is Kevin Renaud with Peerless. Hope everyone had a great Memorial Day weekend. This morning, we're thrilled to have Norm Ouimet in from Krohne to talk about magnetic flow meters, design, sizing, application, installation, and calibration. Just for some brief introductions, today's geography in typical fashion, we're represented by 11 states. It's a great crowd this morning. Geography, you can see the states represented. A lot of different industries here, chemical facilities, engineering, and EPCs. We have OEMs and skid builders, pharmaceutical, power contractors, education, and government. And again, we have some friends in India as well with us this morning. So briefly, Peerless is, while we're proud of our 106-year history, we are a trusted source for components that keep plants operating safely and efficiently and projects running smoothly and on time. Our customer base, again, is diverse, skilled, and quite complex, and we're proud to play the role in any of their challenges. The company has three major segments. Our Procore division works with our OEM customers, engineered skid builders. We have our process group that handles a lot of the MRO type business, chemical, pharmaceutical, and you can see the list. And finally, we have our high temp and fabrication division that works with high temp insulation, refractory, scientific surfaces, and laboratory and medical. So again, to introduce our presenter this morning, it's Norm Ouimet out of Syracuse area. He is the district sales manager for the Northeast. We also have Marty McLean, who is the US sales manager with us. From the Peerless side, we have the normal players. Dan Morgan is our continuous improvement manager. Greg Barrell is our business development guy for the process group. And again, I'm Kevin Renaud in business development as well. So before we get started, briefly, we like to humanize the presenter. And while Norm is not busy at Krohne, he is a blues and classic rock performer. So he does play the guitar and harmonica, and one of his claims to fame is the production of a CD that was released about 10 years ago. So if you like the sound of Norm today, you can find the recording and click the link and go ahead and get your own copy of his CD. So there you have it. And with that, I'm going to turn it briefly over to Dan Morgan, who's going to go over some housekeeping. Dan?
Yeah, hey, thanks, Kevin. Actually, I didn't know that about Norm, and we haven't talked about this, but I did play a little trombone back in 5th and 6th grade. So anytime you want to jam or need a fill-in, Norm, let me know, and I'll step in. But yeah, I just want to mention real quick here to all of our attendees, what I'll be doing today as Norm is presenting is keeping an eye on the questions panel. So if there's anything that you guys have questions on or would like a little bit of additional clarity on as Norm is presenting, please feel free to submit your questions through that panel, and then I'll be interjecting throughout Norm's presentation with those questions, and hopefully give you guys the answers that you need. So please don't hesitate and use that questions panel as you see fit. So with that, I will turn it over now to Norm.
Okay, good morning, everybody, and thank you for joining us today. Really appreciate it. And with that, we're going to be talking about magnetic flow meters, commonly known as mag meters. And you can see here on the list some of the topics we'll be covering as we move along. So, magnetic inductive flow meter, again, commonly known as mag meters. So basically, these are used in pretty much any industry you can possibly think of, as well as in municipalities in water treatment facilities and wastewater treatment facilities. chemical companies, etc. Theory of operation based on Faraday's law of induction. It says a voltage will be induced by a change in the magnetic environment of a coil. So what that means is basically we need three things to produce a voltage. We need a magnetic field, we need a conductor, and we need relative motion between them. It doesn't matter if you move the conductor through the magnetic field or move the magnetic field across the conductor, you're going to generate a voltage. So when we're looking at a mag meter, basically, and I'll spare you some of this stuff, when we're looking at a mag meter, the conductor is the fluid that we are hoping to measure the rate of flow. So we have a magnetic field, we create the magnetic field, and then as the fluid moves through the magnetic field, there's a small voltage. This is in the millivolt range. So we have electrodes that are going to pick off this voltage that's produced and bring it back to the electronics, which we'll talk about a little bit more in a few minutes. So in simple terms, right? Moving a conductor through a magnetic field generates a voltage. That voltage is directly proportional to the velocity of the conductor. So once we know that, if we know the cross-sectional area of our pipe, we know the velocity, we can calculate the volumetric flow rate from that. And that's done up in the electronics of the device. Depending on the direction of flow, you got two electrodes in there. One will have a more positive charge and one will have a more negative charge. So again, depending on which direction the flow is, electrode 1 may be more positive or electrode 2 may be more positive if we reverse the flow. So that brings up a couple of questions. And what I'm going to do here is I'll just give you all a few seconds to think about this, and then I'm going to give you the answer. But first question is, what would you say is the major limitation of a mag meter? And question number 2 is, should a mag meter be able to measure flow in both directions? And again, while you're thinking about that, I'll go ahead and move on. And major limitation is that the medium that is being measured has to be conductive. So if you've got a non-conductive fluid, you're going to have to go to a different technology. You're going to have to go to ultrasonic or Coriolis or some other, maybe a mechanical type meter or whatever. You're not going to be able to measure that with a mag meter if it's non-conductive. By design, all you're doing is putting flow through a magnetic field. Doesn't matter which direction the flow goes in, you're going to generate a voltage. Now, if you want to be able to read that voltage in both directions and do something with that, in other words, are you trying to totalize and subtract if the flow is in the reverse? That's all up to the manufacturer to build that into their electronics to allow you to do whatever it is you need to do if you do have a dual flow situation. Liquids can either have solids or not. Pulps, pastes, slurries, all of these can be measured with mag meters. So the thing I've got in red there, this is a rule of thumb. So a lot of the things that I'm going to show in this presentation are rules of thumb. Are there slight deviations from these rules occasionally? Of course. So we say here that the standard minimum conductivity should be about 5 microsiemens per centimeter. Does that mean I'll never find a mag meter that can read at 3 microsiemens? No, I probably can find one out there that'll read at a lower conductivity. But general rule of thumb is that's where we want to be at that number or higher. So the almost ideal liquid flow meter, okay? Typical accuracy, 0.5%. Does that mean that that is it? No. We've seen mag meters that can measure 0.2, 0.25, 0.3% accuracy. It all depends on the construction. It all depends on the particular model, and you know, the electronics have a big part to do with that as well. There's no moving parts. Pressure drop is very minimal because there's no restrictions within the meter itself. Prices over the last 20, 25 years have come way down on mag meters, so they're very affordable. There's very little maintenance, unless you've got a slurry that's causing some buildup on your electrodes where maybe you need to go in there and clean them once in a while. But other than that, you know, unless you get a lightning strike that destroys the electronics or whatever, maintenance is pretty much nil. Can be used for clean or dirty liquids, and your turn down ratio is typically in the range of 40 to 1, which is, you know, pretty good dynamic range. So how are they constructed? Well, we have a tube. Typically it's made of excuse me, a tube that is typically constructed of stainless steel, okay? And then you can either have a sandwich version with no flanges, or you can have flanges attached to the tube. Both types are available in the industry. A set of coils to produce the magnetic field. We're going to have the electrodes to pick off the microvolt or millivolt signal that is generated. And then we have liners, different materials of liner to isolate the tube from the process fluid. So here's a stainless steel tube with carbon steel flanges. The flanges are not considered a wetted part, which is why they can be made of carbon steel. Coils are added to the outside. Then there are plates to basically contain the magnetic field inside the housing. And then the electronics, you'll have a flow converter. Flow converters can be what we call compact, mounted directly on the tube, such as what you see here. This is a sandwich version that you see here with no flanges. Or you can have a separate converter. It could be a field mount, which is usually a converter that has some type of pipe clamp, so you can just attach it to a pipe nearby, or a wall mount, which will have a bracket to mount it flat on the wall, or even a rack mount, where you can put several of these within a 19-inch rack. The converter needs to amplify that measured voltage because it's very low in the millivolt range, so we need to amplify that signal. Once we amplify it, we need to filter it to separate our actual signal from any noise, extraneous noise that we don't want. And then we need to convert that signal into something we can use, whether it be a 4 to 20 milliamp, or whether we're converting that signal to some form of communication, such as Profibus, Modbus, or Ethernet, but that's all done in the electronics. And then liners, there's a varying amount of liner materials that are used depending on the application. So basically, what we need to do when we're picking out a liner material, the three main areas we need to be concerned with are the temperature of the process fluid, whether there are any chemicals and what those chemicals are, and also whether the material that's being measured is abrasive. So as you can see, when you look down the different liner materials here, some have varying degrees of resistance to abrasion, with obviously ceramics being the best. And then also, if there's a chance that that line could ever come under vacuum, we need to be concerned with that with certain liner materials. Obviously, ceramic is very vacuum resistant, but a Teflon liner will not be. So there's special precautions that have to be taken. The electrodes, just like we have a lot of different materials available for our liners, we also have a lot of different materials available for our electrodes. They can be stainless steel, Hastelloy. Then you can get up to the real exotic metals where, it's going to add to the cost considerably if you're in the tantalum, titanium, platinum region. But sometimes it's necessary, depending on what the fluid is that's being measured. Sometimes we have no choice but to go to a more exotic metal for our electrodes. The other thing that's available in electrodes is something that's called low noise electrodes. And typically what'll happen is the electrodes are coated. Could be a rubber coated tungsten carbide, or as you see there. So what happens, especially when you have a material that has a lot of fibers in it. So for instance, paper stock in a paper mill, a lot of fibers. As these fibers impinge upon the surface of the electrode, it'll create a lot of noise. By putting the coating on there, that noise is minimized very, very considerably to the point where, you really don't have to do a whole lot of filtering to the signal anymore. Because when you do a lot of filtering, you're also dampening your signal, you're also putting in some time delay, and it's really going to affect the quality of your measurement. Grounding. One of the most important things with magnetic flow meters is grounding. Probably 8 out of 10 times when a customer is experiencing a problem, typically it's maybe because the meter wasn't properly grounded when it was installed. So grounding rings is one of the ways of grounding a mag meter, which we'll talk about more in a minute. Or a grounding electrode can be attached to the meter body and use that as the grounding method. If the piping is well grounded and conductive, you may not need any additional things such as an electrode or grounding rings. You may be able to just put a jumper from the meter body over to the other side of the flanges, and that may be good enough. Or something called virtual grounding or virtual reference. So here's a case where No grounding rings were used. Simply, a jumper was put to the other side of the flanges because it was a good ground on the piping material, and that was sufficient. Here's a case where now the grounding rings are in between the two flanges. So here we have attached that jumper to the grounding ring itself, which is a wetted part. So that grounding ring will be at the same potential as the fluid within the pipe. For instance, if this were a PVC pipe, this is the way you would have to do it because you can't ground to a PVC pipe, obviously. So virtual grounding or virtual reference is accomplished via the electronics. What we're basically doing here is we're looking at the potential of the fluid, and we're making sure that nothing on the body of that meter or nothing in the electronics of that meter, we're making sure that no potential difference exists between those components and the actual fluid. And we're doing that via electronics. This is a feature that is an option, typically adds roughly around $300 to the cost of a meter, which on a small meter, that's probably a lot. But if you've got a 60-inch meter and you're having to use exotic metal for the electrodes, that means you're going to have to use that same exotic metal for the grounding rings. In that case, the grounding rings could end up costing as much as the meter, in which case a $300 adder for virtual grounding is a pretty easy sell. Grounding rings are a wetted part, as I have stated, okay, and they're used as a reference for the electrodes. And they must be chemically compatible with the process, just like the electrodes. So there are different styles of grounding rings depending on the type of liner you're using. So on a Teflon liner, there's going to be a grounding ring that is going to protect the inlet side to protect that liner. Also, there's another type of grounding ring that goes on the inlet side of the meter to protect if you've got a highly abrasive material that's going through the meter, that will also help to protect that edge of the liner that the material is coming through. And then there's just your standard flat #1 grounding ring. Flanges, as I said a few minutes ago, are not a wetted part. So typically they can be carbon steel, and then manufacturers will typically just put paint on them or powder coat them, epoxy coat them, whatever is needed. So that leads us to another question. And I'll give you a few seconds to think about this one as well. So it's what should be considered when selecting liners and electrodes for a magnetic flow meter application?
Hey, Norm, just real quick, one question came in, and I think you maybe just touched on it a little bit, but the grounding rings, those would all be available in the same materials to cover any sorts of compatibility considerations?
Absolutely. Absolutely, yes. So if I find that I have to use a platinum electrode, that means I'm going to have platinum grounding rings because both of those will see the process fluid. They're both wetted parts. Absolutely.
Okay, perfect. Thank you.
Okay. All right. So moving on to answer this. So the process that we're measuring is going to dictate which liner and which electrode combination we use. So we need to be concerned about abrasiveness, chemical compatibility, and also we need to be concerned about what the material of the grounding rings will be, as we just stated. Brings us to calibration. So now most manufacturers are going to give you a 2 or 3 point calibration as pretty standard is what comes with that meter. If you have a highly sophisticated application where you want to get as much accuracy as possible out of that meter, you can ask for a 10-point calibration. It's not going to come for free. You're going to have to pay for it. But with a 10-point calibration, all that means is they're actually going to put fluid through that meter 10 times to calibrate that meter at 0, 10%, 20%, et cetera. And they will plot a much more accurate curve than they would with a 2 or 3 point calibration. However, for most applications, it's not required. Again, if you have something where you really require it, it is available at a cost. Again, calibrations can be performed a lot of ways. So for smaller diameter mag meters, we typically see them using a small volume prover or a master meter. Now, if you're going to be getting into large diameter meters, typically you're going to see a tower that is used where the fluid is contained in a tower, and I'll show you that in a couple of minutes here. So then there's a count of the volume that's recorded as fluid is allowed to go through. And what that does, it gives them a meter factor or correction factor. And how that number is used varies by manufacturer. Some simply incorporate it into the programming of the device, into the electronics as a correction factor. Others will use it as a calibration number. Depends on the manufacturer exactly how it's used, but knowing that number will be able to allow us to have that device set to give us the stated accuracy that the manufacturer tells us it is capable of. This is a small volume prover, okay? So a known volume of liquid is pushed through the meter, and basically we measure what the electronics recorded based on that known volume, and whatever the difference is, that's going to be our calibration factor. If we're successful, we issue a calibration certificate. We need to, again, as I said, smaller diameter meters typically will use this. Okay, the position of the piston displacing the water is going to come into play. So here's what one actually looks like right here. Okay. Now, if we're dealing with larger diameter meters, then we're going to have a tall tower, and we're going to fill that tower with liquid, and then we're going to release that liquid. And what's going to happen is we know that in between those two switches, in between the high level switch and the low level switch, there is a known volume of liquid. So meanwhile, the electronics of the meter are recording the flow, and we want that flow to be as close to that known volume as possible. Sorry about that animation, it is a little bit slow. Okay,
Actually,
so
Norm,
we
you know
stop
what?
counting.
Oh, sorry. We did have a couple of questions come in. If now's an okay time.
It's okay. As soon as the water stops flowing here, hang on. Okay, we're good there.
Yeah,
Okay, sorry
all right.
about that. Yeah, sure. Go.
So kind of going
What were
back
the
to the conductivity, can these
question?
types of meters actually be used to
You say you had a question?
display? Yeah, can you hear me? Can you hear me, Norm?
Yeah, I'm sorry, you're breaking up on me a little bit.
Okay. All right, maybe we will reserve some questions.
I didn't
for the
catch
end.
that. You were breaking up on me a little bit. I'm sorry about that.
All right, why don't you go ahead and we'll circle back to the end.
Okay,
Yep.
so now we see that there's a, okay, so we see that there's a slight deviation here between the known volume and the measured volume, and that is what's going to give us the uncertainty, and that will, from that, we will get our calibration factor that we'll be able to insert into the configuration of that meter, and we will then be able to obtain the stated accuracy of the device. So when we get the we will get a wet calibration report. We need to have traceability of the calibration rig. ISO accreditation is what is typically used internationally. And we need to know the accuracy of the calibration rig. So why do we require a wet calibration report? Well, I'm not going to ask you to answer that one. I'm going to tell you, because without that, there's no way to accurately judge the meter's performance. Why do we require traceability of the calibration rig? Because that tells us that the rig itself has been calibrated and that it is accurate. Why do we require ISO certification? Because ISO not only certifies the calibration rig, they also certify the technicians that perform the calibration. They have to go through some rigorous training and testing, and they also get certified through ISO. So now we know that we have an international standard that everybody is abiding by, and we can feel pretty comfortable that our meter has been properly calibrated. Why do we need the rig to be accurate? Well, again, if we're trying to get 0.15% accuracy on the meter, we can't do that with a rig that's only 0.17 accurate. So we always want one order of magnitude difference between the rig and the meter that we're trying to calibrate. So the rig obviously has to be much more accurate than the accuracy we're trying to obtain from our flow meter. So sizing. So one of the typical things that comes up all the time, and it happens quite often, you get a phone call and somebody says, hey, give me a price on a 10-inch mag meter. So then you start asking them questions and, well, why do you need a 10-inch meter? Well, because it's 10-inch line. Well, okay, what are your flow rates? So now as you get into it and you ask them questions, we need to know what the flow rates are. We need to know all the conditions, because just because it's a 10-inch line, they may very well only need an 8-inch meter based on what their flow rates are. Because the thing is, if their flow rates are not high enough, the velocity will be too low. And if we get below a certain velocity, the accuracy of our meter isn't going to be all that good. So for instance, here's an 8-inch meter. So over here on the y-axis, this is the percent of error, okay? And down here, this is flow in gallons per minute for an 8-inch mag meter. So we see that when we first start out, we've got quite a bit of error here. As we come down, roughly around 500 gallons per minute, we get into the sweet spot of that meter where we're probably at about 0.5% accuracy. And as we increase and get up to the actual capacity of that meter, which is roughly about 5,000 gallons per minute, now we're at about 0.25, 0.3% accuracy. So you can see that if your velocity is too low for that meter, it can vastly affect your accuracy, okay? And your error margin goes up. And then you're calling the manufacturer and saying, hey, you told me I was going to get X amount of accuracy, and I'm not getting anywhere near that. So it's important that the meter be sized for the actual flow conditions and not necessarily for the size of the pipe. Lower the velocity, the smaller the voltage, okay? So roughly, and again, this is a rule of thumb. This is not a hard, fast thing here. 30 millivolts per 3 feet of velocity through the meter. 6 feet per second is 60 millivolts. 1 foot is 10 millivolts. Again, will that vary slightly from one manufacturer to the other? Of course. But this is a good rule of thumb to keep in mind when you're looking at designing systems. In the wastewater industry, velocities are normally 2 to 8 feet per second, can be as high as 12. They're trying to keep solids suspended so that they don't build up. They don't want it too fast either, because then you'll cause a lot of abrasion. So they're always trying to keep within a certain range. In potable water, rates are typically a little bit higher because you don't have to worry about suspended solids there. And everything is dictated by the National Sanitation Foundation. They approve all potable water applications. Most magnetic flow meters are designed to operate when full, which means that if the pipe is not full, if there's air there trapped in that pipe, we are not going to get an accurate measurement. So if we're only at 3/4 full in the pipe, we can probably assume we got 25% error. Now, it does say with a few exceptions. There are some meters on the market that can read a partially filled pipe. Typical guidelines for a standard mag meter. We typically want 5 diameters of straight run upstream from the meter and 2 to 3 diameters downstream. And that is typically measured to the center of the flow tube. So if this is a 10-inch meter, we want at least 50 inches of straight run measured to the center of the flow tube on the incoming side and 20 to 30 inches of straight run on the outgoing side. Does that mean the meter won't work if we don't provide this? No. Here's a case here where a customer knew that they were going to have a very difficult installation. They asked the manufacturer to replicate this in their test facility, and they did. They replicated this in their test facility so that they were able to calibrate that meter and get as much accuracy as they could out of it based on actual conditions. But this is not a normal installation right here. Don't think that that's anywhere near normal. So meters located in high points of piping runs, okay, because of trapped air, you can see extremely high flow rates, right? Because part of that, the electrodes are reading a certain velocity and generating a certain voltage. But if 20% of that cross-sectional area is air, there's no fluid there. So it's really giving you too high of a measurement. Again, you're displacing a significant portion of the fluid if you've got trapped air, and the electronics will miscalculate the flow rate. So in other words, we're talking about a condition that would be something like this, kind of an exaggerated one, but that's what we're talking about. The electrodes are still covered with fluid, So they can still measure, but they're measuring based on the cross-sectional area here, which half of that cross-sectional area appears to be air right now. Again, installation, sometimes people will turn the meter because they don't know what they're doing. They turn the meter because, oh, it's going to be easier to, install it this way. Well, what happens now is instead of your electrodes being at 3 o'clock and 9 o'clock, they're at 6 o'clock and 12 o'clock. That can be a pretty bad thing as well, because, as the flow goes through there, and if you do get any kind of an air gap, it'll be magnified even more in this case, because one of the electrodes could end up totally out of the fluid altogether, and then you're just not going to get any kind of reliable measurement at all. So what we're looking at is the flow profile, right? We want a nice uniform flow profile where the highest velocity is in the center of the flow and the lowest velocity is on the walls of the piping. Okay, so distortions can occur for a lot of reasons, right? We have a partially closed valve that's too close to the meter. When the gaskets were installed, the part of the gasket is hanging out into the flow. It wasn't installed properly. There's a 90-degree elbow or a T that's too close. We don't have the proper amount of straight runs. So then we start getting turbulence instead of a nice laminar flow, okay? Distorted fluid velocity, okay? This is one of the most, that and improper grounding are two of the most common reasons for inaccurate measurements, okay? And this can be caused by all the things I just mentioned a minute ago. So if we're going to go and size a magnetic flow meter, what information do we need to provide to the manufacturer so that their technicians, their inside sales engineers, can accurately size that meter for us? Number one, we need to know that we've got a conductive fluid. Number two, we need to know what the minimum and maximum flow rates are going to be. We need to know that range. We need to know what the pressure rating is going to be. What temperature will the fluid be? Do we want a flanged or wafer style meter? Do we need approvals? Do we need stuff like factory mutual or any of the European approvals or any other approvals that may be out there? Again, the NSF or whatever. Do we want the electronics to be compact, mounted on the flow tube itself, or do we want them remotely mounted? And if we are going to remotely mount them, how much cable will we need? Because a lot of times that cable is installed at the factory. And sometimes in a situation where we have IP68, where the cable goes into the junction box on top of the flow tube, it will be fully potted. So being able to extend that cable in the field is not easily done. Will we be supplying the meter with AC or DC? And what output requirements do we have? Do we simply want a 4 to 20 milliamp signal? Do we need HART? Do we need Modbus, Profibus, Ethernet? What do we need? So both of these installations right here would be acceptable with the flow going in this direction. The best is to have the meter vertically mounted with the flow going up, because then you know you'll always have a full pipe. If that can't be done, then the next best thing is to have it horizontally mounted. This is not good. This will cause air cavitation. And with the flow going down is really probably about the worst way you could install one of these. Slightly inclined, some of these are good. Sometimes if we cannot ensure that the meter will always be full, this type of piping arrangement sometimes is done simply to be able to keep that meter flooded and ensure that will always be full. Sometimes we need to have a little bit of back pressure on the meter to ensure that it's always full. We need to avoid vibrations, excessive vibrations. We need to avoid strong magnetic fields. That is, magnetic fields not related to the meter itself. And again, the mounting position, right? We talked about this. It's okay to have the junction box underneath because your electrodes are still at 3 o'clock and 9 o'clock. But to the right or to the left, not good, because the electrodes are not properly positioned at that point. And again, distorted flow profile. As I mentioned, if we don't have a nice laminar flow, if we're too close to a 90-degree elbow, our higher velocity fluid is closer to the wall than being in the center where it belongs. That is going to cause a flow distortion, and that will cause our meter to not read properly and give us the stated accuracy. Again, Flow disruptions can add as much as 1.5% to the error rate. Okay. Vertical piping with flow moving upward is preferred, but not always possible, and we understand that. What if you cannot provide an adequate amount of straight run? Well, I hit on this a little bit a few minutes ago, but again, if you can't provide enough straight run to smooth out the turbulence, you're going to have to live with the inaccurate effects. So that doesn't mean that you've got a meaningless reading at this point, because you're going to have a measurement that's very repeatable. And in some processes, repeatability is more important than accuracy, or as important. So if we know that it's a repeatable measurement and we know that we're off by, say, 1%, a lot of times we can account for that extra error within our DCS or PLC system. Do not tie the grounding ring into the electrical ground of the building, because you're likely to pick up some noise. So you want to have a separate ground. If you've got in a case where you may even want to go and put your own ground rod in and then ground to that. Or, if there's a grounding grid, rather than go back to the electrical panel, go to the grounding grid itself that may be embedded in the concrete. You want to try to avoid picking up any additional noise at all. And you will pick up noise. If there's any potential difference between the fluid potential and the ground that you're connected to, you will get some noise. So you want to avoid that. I/O, 4 to 20 milliamp output, frequency output, pulse. Again, a lot of different communication buses. Some of your serial 232, 485. There may be relay outputs where we can simply get a contact closure at a certain volume or whatever. And we can also have a control input. So if we wanted to, say, be able to reset the totalizer of that meter from our PLC or DCS system, from the HMI SCADA, we would be able to ask for that kind of an input from the manufacturer and be able to wire that in so that that totalizer can be reset from the SCADA system. They're pretty trouble-free. 10 to 15 years is not unusual. Here's one that's almost 40 years old. Some have been known to last for years and years and years without any trouble whatsoever. Maintenance, verification. There are a lot of different tools available depending on the manufacturer. There are things like MagCheck and CalMaster and OptiCheck, etc. These are tools that can be connected to the meter to do a verification that, number one, that the coils are still intact, that the liner is still performing, and then there's also tools to check all of the electronics within the converter. Resistance checks are done from coil to ground to make sure we don't have any leakage paths where maybe some insulation has been compromised or something of that nature. And then from each electrode to ground, etc. So some of these can simply be done with a meter, with a typical multimeter. Some of them will require a little bit more sophisticated tool. Okay, and again, a lot of this is what's being checked: wiring continuity, tube integrity, etc. Again, there's a simulator that is then connected to the electronics to simulate the signals that it would normally receive from the electrodes. And by imitating those signals, we're able to check that the electronics are still healthy and operating as they should. We can then, from a lot of these tools, a report can be generated. Typically, it's a PDF file that'll give us the parameters of how the testing went. And we can always compare this to the original calibration certificate to make sure that we're still within specification. Again, for those of you old timers out there, a Simpson analog meter can be used. I still own a Simpson analog meter, Simpson 260, or you can use an electronic fluke type electronic VOM to do some of the checks as well. So why do we want to use magnetic flow meters? Well, for all the reasons listed here. They're pretty easy to install. I say mostly. There have been some challenging installations. I've had to really, think about it on how they were going to install that meter. But typically, they're easy to install. They last a long time. They're very maintenance-free. They can be used in a wide array of applications. Very low pressure loss, and their accuracy is pretty darn good. Where can I use them? All of these places, right? activated sludge, dewatering, sludge, effluent, collection system, lift stations, all types of applications, chemical feed, right? Water pre and post filter within a filtration plant, right? RO water may not be conductive enough. So that is something that we really want to be careful with. If we are dealing with RO water, we want to know what the conductivity of that fluid is. And you may not be able to use a mag meter. You may have to go to a different technology there. So here's a 24-inch meter on a lift station. So here's the mag meter with compact electronics mounted right on the meter. Now here's a clamp-on ultrasonic meter that's been strapped to the other pipe over here, and that is the electronics for the clamp-on, which this is most likely a temporary installation. It's probably simply being used as a check against the other meter. So this may be something they do on an annual basis themselves on site, or they may have some other organization that comes in and puts that on there for a period of time, and then they record what's going on and they check that against the other meter. And that's a simple check that can be done just to make sure that the meter is still within its original tolerances. And having said that, I am going to now open this up to questions and or comments.
Thanks, Norm. Yeah, hopefully you can hear me now. We do have a couple of questions, but if you're still having trouble with the audio, I believe Marty is available to jump in here and can give some answers here if
right now
needed.
I can hear you. Right now I can hear you just fine. That's, you know.
Okay. All right. We'll start here. So going back to the first, beginning part of the presentation, can this type of meter be used to actually display the conductivity of the fluid that's passing through it?
Yes, that is one of the parameters that's available within the electronics. You can go in and look at the conductivity of the fluid. Absolutely. And again, now, that doesn't mean that that will be available on every single electronics out there, okay? Depending on the manufacturer, they may have some lower end electronics that they sell at a much reduced price that may not give you the conductivity. But yes, there are electronics that will show you what the conductivity is, absolutely.
And the conductivity, if I can just chime in there, the conductivity may be off a little bit versus an actual conductivity probe, but you can get an output from some electronics that will eliminate the fact of putting in another leak path, a potential leak path in your process. So.
Cool. All right. Thanks, guys. Next question here. So how do grounding rings, if used, protect a PTFE liner?
Well, because the grounding ring has a lip on it, and when that grounding ring is put on the inlet side of that meter, that lip will actually cover and protect the edge of that Teflon liner so that the fluid coming in is not impinging on the actual edge of that liner.
Got it. Okay.
That's a number 3 grounding ring where it looks, if you saw in Norm's drawing, it looked like a little top hat almost that goes into it.
Yep.
So it helps hold it in place, especially when vacuum might be present.
Perfect. Okay. Then we have some questions about accuracy here. So one of the questions is, do these meters have a consistent accuracy with a varying fluid conductivity, especially like down to the lower limits of the conductivity?
Well, any meter is going to have a stated range of conductivity or a stated minimum conductivity that it requires. If you get below the stated minimum conductivity that the meter is capable of measuring, sure, that's going to affect your accuracy. But there is some tolerance. I mean, if a manufacturer tells you that, hey, this can read down to 4.8 microsiemens per centimeter, it can probably read down to 4 or 4.1 just as well. But they're not going to go out on a limb and give you the absolute limit. They will always have a little bit of margin of error within their stated accuracies and stuff there. So typically, if it's a small variation, yes, you're still going to get accuracy. But if it's a huge variation, no, it's going to affect the accuracy, obviously.
Got it. Okay. So we got a question here that's a little application specific. So hopefully, you're familiar with this type of application. So can something like AKD size in paper making applications going in very close to the meter disrupt the signal?
Typically, if you're going to add any kind of other fluid or any kind of a chemical, we typically want you to inject that after the meter. Because what can happen is if it's being injected too close to the inlet of the meter, it can affect the flow profile, right? It can cause some distortion in the flow profile if you've got some other stream coming in, such as injecting a material such as this gentleman's asking about. So we typically don't recommend injecting anything at the inlet side of the meter. Now, if it's downstream far enough, or upstream, I'm sorry, if it's upstream far enough from the meter where it's not going to cause a profile distortion, oh yeah. But if it's right there at the inlet of the meter, chances are you're going to cause some distortion in the flow profile, and it will affect the way that meter measures. We typically want you to do that after the meter.
Got it. Okay, so let us know if there's any follow-up to that one. And then we have one more here. It's a bit of a fun one. So before I turn it over to Kevin to wrap things up, your last question is Muddy Waters or BB King?
Well, I never had a chance to see Muddy Waters live, but I saw BB King several times live over the years. And one quick thing, I saw him live in Saratoga, I don't know, 15 years ago, maybe 20 years ago. And the Buddy Guy was the opening act. Buddy Guy tore the house down. And my friend and I are sitting there saying, how the hell is BB going to follow this? How do you follow this act? BB King came out that night, played better than I had ever heard him play before. So I got to go with BB only because I never got a chance to see Muddy live.
All right, fair enough. And actually, one more question did came in, so I guess bring us back to reality a little bit here. Can you maybe just run through very quickly again the virtual grounding situation? Maybe just a little bit of clarity on like why you would use something like a ring if you can just use the virtual grounding.
Well, because on a smaller meter, if you've got like a 2-inch meter, the grounding rings are going to be pretty cheap. So why would you want to go to a $300 adder for virtual reference when you might be able to pick up a pair of grounding rings for 75 bucks or something? You know what I'm saying? It comes down really to a cost benefit situation. That's why I say in a larger meter, and especially if you're having to use exotic metals in those grounding rings, they can get quite expensive. So going to virtual reference, and again, virtual reference is typically only available on the higher end electronics as well. So there will be another slight, so if you are going with a lower end electronics to save money, you will have to go to that higher end electronics in order to get the virtual reference option. So the option itself is about 300 bucks, but you could end up spending a few hundred more for that higher converter. Okay, so again, it's a cost benefit situation, right? So on a small diameter meter, in most cases, it doesn't make sense.
Got it.
But as you get into the larger diameters, yes, it definitely makes sense.
And in a lot of cases, for
ahead,
example, we've had some issues where somebody wanted 42-inch grounding rings and they wanted them made out of titanium or tantalum. I mean, obviously the $300 that Norm's talking about, at least in our situation, was the better route to go. But the virtual is there. The other thing I just want to make mention of, it's only available in 3/8 inch in size or above, and we need a minimum of 150 microsiemens for the virtual reference to work properly.
Right, so you do need a higher conductivity. I'd forgotten to mention that. Thanks, Marty.
Yeah.
Okay, that's all the questions we have so far. But again, we'll be here for another minute or two. So if you have anything else, please continue to send it in. And if we don't get to it, we can obviously follow up with you after the presentation. But for now, I'm going to turn this back over to Kevin just to wrap things up briefly.
All right, well, once again, we'd like to thank everybody. Norm, nice job. Thank you very much. Marty, thanks for being here as well. We do appreciate the support. Again, if you have any lingering questions and you want to come back, this will be recorded. You'll find it on our website. And next week, I will say that we are going to be back with Riotemp, and it's going to be about pressure gauges and preserving the longevity through both diaphragm seals and understanding the difference between pulsation and vibration. So with that, again, if there's any lingering questions, you can keep on sending them in. We'll make sure we get back with Marty, get back with Norm, and we'll respond to you quickly. So again, thanks everyone. Stay safe and enjoy the week.
Thanks for
Hey,
your
thank you,
attendance and
everyone.
thanks for the opportunity, Kevin. This was great. I enjoyed
You
it.
got it. Thanks again, guys.
Yep. All right, bye, guys.
Take care, everyone.